I am very happy to be welcoming Professor Eldar for this week's One World Minds talk. She holds an appointment in both the electrical engineering and the mathematics and computer science departments at the Weizmann Institute of Science, where she is also the head of the Biomedical Engineering and Signal Processing Center. Her highly cited and incredibly influential work spans sampling, analog to digital design, AD design, medical imaging, communications, systems, computational biology, compressive sensing, and a wide range of other interesting inverse problems where she's done a lot of work. She has numerous awards and has been a visiting professor at many places, including recently, I guess, at MIT and Duke University as a visiting faculty member in the past several years. So I am extremely happy that she's here to tell us what she's been working on recently, and I will shut up and turn things over to her. So thanks for coming.
Okay, well, thanks so much, Mark, for the invitation and for the really kind introduction. So I really appreciate it. And it's like we were saying, it's a really nice opportunity, despite the circumstances, to get to talk to so many of you. So I hope everyone's doing well and safe and somehow still able to celebrate the end of the year together. So today, as everyone knows, we live in a digital world and we're generating more and more data, more and more bits. And what I want to talk about today are some ideas that we, and of course, many, many others also in this community, and I'm sure on the Zoom, are working on, where basically we want to see how we could do this acquisition more efficiently. And we're going to focus on some of the main ingredients of signal processing, looking at tasks, looking at structures, looking at models, and we'll see how we can put these ideas together, including also newer ideas like deep learning, in order to come up with efficient systems. And we'll also see that these can have applications beyond just the math and engineering in different areas of medicine and science, which are areas we've been focusing on a lot recently, particularly in medical imaging. So today we're generating more and more data. Data is all over the place. And, we take this for granted, but this actually is quite expensive and it creates different bottlenecks on the system. So for example, we know that there's data centers just to store this data. In fact, I actually looked this up. There's 3 million data centers worldwide. So I think that's a little bit scary, right? You see one of these data farms in Finland. So, you have millions of these buildings all over the place that are just storing data. It consumes a massive amount of power. So we know that the power consumed by the IT sector exceeds the power of some of the big countries. Processing it is very difficult. Communicating it is very difficult. And in fact, in a recent quote by Cisco, they said that the internet traffic will approach a zettabyte, which is 10 to the power 21. Okay, so it's a number that you can't even imagine by 2022. So, and that was before COVID. So I imagine that COVID, of course, made that kind of jump up. So, that's an enormous amount of data. And the question is, do we really need all of this data? Now, why would we think that we don't need all of this data? Well, there's many applications where we know that we're taking more data than we're actually using. So if we look, for example, at medical imaging, whether it's MRI, CT, or ultrasound, we're basically acquiring physical signals. So let's say in ultrasound, we have many elements within this probe. And in each one of them, we're acquiring a physical signal. But at the end, when we make a medical diagnosis, we're doing it based on an image. So all of this physical data is projected onto an image. And this is true in other imaging modalities as well. So we're not using all of this data that we actually acquired. If we look at smart cities or autonomous vehicles, which is another very popular area in recent years, what people are doing are putting more and more sensors. So we have, LiDAR, LiDAR, vision. So we have more and more sensors. They're acquiring all of this physical information all of the time. But at the end, when we make decisions like, where should the car turn, it's being based on a much projected version of all of this information. Deep networks are another really great example. So we know that we could train deep networks, for example, to classify, let's say, between a cat and a dog, but it requires a lot of information, a lot of training data, whereas a little kid could see, 2 images of a cat, 2 images of a dog, and immediately classify. In fact, they could even look at images in a book, and then, when they're outdoors and see a real life cat, they'll know that it's a cat. So obviously, we're not doing things efficiently. And that really is what we want to focus on and ask, you know, is there a way to acquire only the information that we need? Girl, in a digital world. So this is a song I really like by Judy Gorman that kind of really, you know, goes into this essence of analog to digital conversion. So when we say acquire, of course, we have to physically acquire these signals. So we have continuous time signals that we're interested in. They go through an ADC, an analog to digital converter, which is, of course, a piece of hardware. So we actually have to design this thing. And at the output, we get a bunch of bits that we're going to process. And as everyone knows, you know, standard ADCs are based on the well-known Shannon-Nyquist theorem. But what we do in an ADC is that we first sample in time, and then we quantize the amplitudes. So the sampling is typically based on Shannon-Nyquist that says that we have to sample at least twice the highest frequency, and soon we'll go also into the quantization. So these are the basic principles of ADC design and of analog conversion. Now, in fact, if we look at how systems are actually built, they're built today in modular form. So we have a continuous time signal, let's say the signal coming from an ultrasound machine. We're first going to sample it based on the Nyquist theorem. Then we're going to quantize, and there's many different rules of quantization, but as a rule of thumb, we could, a popular rule of thumb is that for every 6 dB that we want in SNR, we have to add another bit. So we apply this quantization rule. And only at this point, after we quantize, do we take into account the actual task that we want to solve. So for example, in ultrasound or in radar, where we sample multiple signals, the task is typically going to be beamforming. So we're going to take all of the channels, add different delays to them and sum them up, and that will end up giving us an image. So we have this very modular way of designing systems where each block is optimized separately based on its own design principles. So this, of course, works, and that's how we have digital systems and digital signal processing today, but it comes at a price. So this leads to very high sampling and processing rates. We've said already that we have to sample at the Nyquist rate when we break this up to blocks. But of course, if we want to get high rate communications or high resolution, then the Nyquist rate could be quite high. When we sample at a high rate, we also get a lot of samples that we have to communicate and process. So that becomes very costly. And if we look at medical imaging, which again is an area that we've been focusing on a lot, then this has other trade-offs. So it requires long scanning times or high radiation dosage. So at the end, this ADC that we kind of take for granted, and it's our gate to the digital world, it actually leads to a variety of different bottlenecks. So the question is how we can overcome these different bottlenecks. So what we want to propose today is a different way of designing these systems. And what we do is we use several guidelines. So first of all, we want to design them jointly. So rather than optimizing each block separately, we want to look at joint designs, where in this joint design, we're going to take two things into account. So the first is the structure, and the structure could be structure in the input itself or actual structure in the system. And the other is the task. So for different types of tasks, we might need different sampling and quantization rates. Now, what we're going to see is that by taking into account the structure and the task, we could actually come up with much more efficient design of systems. And we'll also see that these same principles could be used for problems that are totally digital, so not necessarily just for conversion. For example, we're going to see how this could lead to deep networks that are model-based. So this will lead to model-based or interpretable deep networks that could be very efficient as well. So this is really kind of the main idea of what we're going to be talking about today. And some of the things everyone is familiar with, like compressed sensing and sub-Nyquist sampling, et cetera, are a subset of this. But here we're looking at much broader design considerations that don't necessarily have to do only with structure, and they're not focused only on the sampling, but also on the other points of the system. So just to give some idea of the advantages we could get, and we'll see some of these examples throughout the talk. So this could lead to devices that have much better imaging and are much smaller. We've worked a lot on ideas in the context of MRI, leading to fast and quantitative MRI, efficient wideband sensing and communications, high resolution radar. We'll talk a little bit about efficient massive MIMO systems, joint platforms for radar and comm, because each one of them is done more efficiently. We can combine them. We'll see a little bit how this leads to ideas of super resolution. And finally, at the end, of course, depending on times and questions, we'll spend a few minutes talking about how this also leads to interpretable deep networks. So these are some of the advantages that we could get from this approach. So let me more specifically point out the outline of what we're going to be talking about. So we'll start with looking at structure, and these are ideas that I'm sure many are already familiar with, but we'll look at them in a little bit of a broader perspective. So these include ideas of compressed sensing and sub-Nyquist sampling, and we'll see a little bit of how that could lead to, for example, an efficient wireless ultrasound system. We'll then move to exploiting tasks that do not necessarily rely on structure, but actually exploit the tasks that we're interested in. And we'll see some applications to power spectrum estimation, to communication applications, super resolution. We'll also talk about task-based quantization, so how quantization comes into play into these different networks. And then we'll end by talking about how these ideas could be used in model-based deep learning systems. So that's the plan. If there's any questions, as we said, feel free to jump in and just ask. All right, so let me start by talking about how we could exploit structure and move to what we call sampling, which is compressed sampling, basically by using structure in the input or in the system. And what you see here on the slides are different systems that we've actually built in the lab following these ideas. So these are not just theoretical ideas, but they can also lead to practical systems. So one of the earlier examples that we started off with was this problem of multiband communication, where you have different users sharing a joint system. Each one of them has a narrow transmission, but they could be spread over a wide band, and you don't necessarily know the carrier frequencies, or they may be changing in time. Now, of course, any signal of this form could be looked as band limited to some F max, but if you treat this as just a band limited signal, then you're going to end up, of course, sampling at the Nyquist rate, twice F max, and you're not actually exploiting the structure, because when you sample at twice F max, you're basically accommodating signals that could occupy the entire bandwidth, even though your signal is never going to look like that. So, of course, to be able to exploit this structure, we have to have a good model and then a good piece of hardware that will actually exploit it in practice. Now, the original problem we looked at started from communication, but in recent years, we've also been looking at the same ideas applied to imaging problem. For example, multispectral imaging or multispectral CT, where again, you're using multiple frequencies for imaging. Another class of problems, which actually originated in the really nice work in Martin Vetterli's group on finite rate of innovation, are problems that have to do with streams of pulses. So in these types of problems, you send a pulse, for example, in radar, you send a pulse, and then you're going to get reflections of this pulse every time it hits a target. So what you view at the receiver are a stream of pulses where you want to figure out the times of arrival, that will tell you the distance to the target, and the amplitude, which will give you a sense of the velocity. Now, the same model appears in ultrasound. Again, here you want to exploit the fact that there's a stream of pulses and it's not just an arbitrary signal with the same bandwidth. So if you look, for example, in ultrasound, we get something very similar. We send a pulse through the ultrasonic probe. We get reflections every time it hits a boundary in the tissue. And to plot a line in the image, we're basically plotting these times of arrival. Now, if we could take into account the fact that it's pulses, then we could both reduce the sampling and quantization rate, but we can also get better resolution. We'll talk later about super resolution in this context as well. Now, the ultrasound problem is actually more involved than what we've just shown, and that's because within the ultrasonic probe, you'll typically have tens or hundreds of elements because the ultrasound environment is very noisy. So you're going to get the receiver in multiple elements. And what you want to do is not only sample it, but you also need to beamform it. Basically, you get these signals, you're going to delay them and sum them up in order to increase SNR and increase resolution. So here, the task is not only to sample at a low rate, but to do all the processing at the low rate as well without interpolating back to the high Nyquist grid. And what we're going to see is that not only can we do the sampling at a low rate, but we can also do all of the processing or the beamforming at the low rate. And this will give us a variety of different clinical advantages. So we'll see that it could lead to a wireless ultrasound. It could lead to increased frame rate, for example, in cardiac imaging. It could pave the way to 3D imaging and other clinical advantages that we'll talk about when we go into the applications. Okay, so there's many more examples. Those were just a subset. Of course, what's interesting at the end is how do we characterize these types of signals and how do we turn that into a working piece of hardware that could sample at a low rate. So what we can show, and again, this is earlier work, is that all of these different examples and many more could be viewed within a mathematical context of a union of subspaces model. So what this means is that we know in advance that our signal lies in some low dimensional subspace, but we don't know in advance which low dimensional subspace. So we're given maybe even an uncountable number of subspaces. We know that our signal is in one of them, but we don't know which one. And the basic theorem that paves the way to sub-Nyquist sampling says that if our signal lies in a union, then the minimal sampling rate is the rate associated with the sum of two subspaces in the union, irrespective of how many options we had. So the Nyquist rate will be the rate associated with the sum of all subspaces. And what this theorem says is that you only need to account for the sum of two subspaces, which is what enables sub-Nyquist sampling. So here we're explicitly exploiting structure in the input. So that was a mathematical theorem that says that that's as low as you can go, but it doesn't tell us how to get there. And over the years, we've developed this sampling paradigm, which is a hardware paradigm that actually allows us to achieve these minimal rates. And in a nutshell, what we do is we take the signal, we multiply it by a periodic function. And what that does basically is that we know that any periodic function in time is going to be a stream of deltas, a stream of Diracs in frequency. And therefore, what it's going to do is it's going to alias our data. So for example, in this multiband problem, after we do this multiplication, we're going to be aliasing the data all over the spectrum. So we take our data, we shift it all the way to the right, all the way to the left, and sum up. And this is true more generally. So if we have a union of subspaces model, what we're going to do is we're going to alias all of those possible subspaces. So basically we mix them and overlay them on top of each other. And then after doing them, we could just low pass filter and sample at a low rate. So this basically allows us to sample at a low rate using very simple analog components. We don't have to come up with new samplers. We're basically just mixing, low pass filtering, and sampling at a very low rate. So that's what we're doing on the analog side. In the digital side, after we've sampled, we use ideas of compressed sensing in order to recover. So we're not using compressed sensing to sample because compressed sensing is a digital theory. We're using these analog principles to sample and then ideas of compressed sensing for the actual recovery. So what you see here are some boards that we've developed over the years for different applications. And they're all doing the same thing. They're just designed in different frequency ranges depending on the different problems that we're looking at. So the nice thing is that it's very simple block diagram and it translates into very simple hardware. Now, over the years, we've been able to show that this is actually optimal under several different criteria. So first of all, we can show that this paradigm always achieves the minimal possible sampling rate. We can show that it does it in an optimal way from a mean squared error point of view. So from all sub-Nyquist methods, this will lead to the minimal mean squared error. And in a communication context, it will always it would also minimize the worst case capacity loss. So there's different forms of optimality that we can show for this particular form of sampling in the presence of noise. Now, as I said, of course, for recovery, we rely on ideas of compressed sensing. So I'm sure everybody here knows what compressed sensing is. So I guess there's no need to delve into the compressed sensing details. But I do want to point out that when we look at more general problems beyond the basic sparsity problems that we've looked at, when we started doing this work, the compressed sensing tools need to be extended. So when you look at practical problems, the basic linear model, linear sparse vector model that we're used to from compressed sensing is not necessarily valid. So there's many problems, for example, where we have nonlinear measurements, particularly in the context of optics. There's many problems where we have multiple measurements, but they don't necessarily have the exact same sparsity pattern. They vary, you need to track it. So we've looking at nonlinear sparse recovery. There's been, of course, a lot of work on that by many people. We've looked at sparse recovery when we have a reference. This is true, for example, in MRI where you have multiple images. We've looked at tracking, which is true, for example, in ultrasound, where basically you have a scan, a video where you're tracking, let's say, blood flow. So the blood is flowing over time, and therefore the sparsity pattern is moving, but it's moving according to equations that you actually know. There's been a lot of work by us and many others on statistical sparsity when you have different distributions on the sparsity pattern. And in recent years, and I know there's been a few talks on that already in this forum as well, there's been a lot of beautiful work on using deep learning to to recover. So even when we know that there's sparsity, instead of using the standard, L1 or other types techniques, using deep learning tools, and we've been looking at this as well. And the advantage of the deep learning tools is that they also allow for broader types of structure. So it doesn't have to be a very structured sparsity like we're used to. We can look at more general forms of sparsity. So I'm not going to go into these. I know there's been multiple talks about these notions, but of course it combines with what we were showing before. So we still keep the analog side as we've shown, and then we can use these more sophisticated tools in order to do the recovery. So if we combine these notions, the digital tools that we've just showed and the analog principles that I've alluded to before, then we can show that in many different applications, we could sample and quantize at much lower rates than people are doing today. And we could also be much more flexible in the assumptions on the input. So we don't necessarily have to have strict sparsity. We could be more flexible in terms of what types of applications this could apply to. And in our books, we go into much more detail on the math behind all of this and the actual implementations. So this was summarizing kind of older work, but putting it into the context of what we're going to be talking about in the rest of the talk. So I want to delve into some applications, which will highlight some newer applications that we've been looking at where these ideas are applicable, and then we'll move into the other forms of both looking at the quantization and the tasks. So before I do that, any questions on what we've spoken about so far? All right, so I just want to encourage people to feel free to kind of jump in. All right, so let's delve into some applications, and really a motto in our group is, this quote by Albert Einstein, who says, in theory and practice are the same. In practice, they are not. And we're not disagreeing, of course, with Einstein. But what we try to do in the group is basically close that loop. So, the first equations you write down never describe what happens in practice, but by building the prototypes, we actually learn a lot about the problem, correct the theory, and then eventually the practice does meet the theory. So what I'll show you now are different devices and applications that we've looked at that really follow the principles that I've showed right now, and hopefully will convince you that this does work in practice as well. So the first application I want to show, just because I happen to really like this application, is to ultrasound imaging. So in ultrasound, we've shown that we can actually sample at 4% of the Nyquist rate using these ideas. And this leads to a variety of interesting clinical applications. So it paves the way to 3D imaging, which today is really limited by the data rate. It allows us to do things much quicker, which is important, for example, in cardiac imaging. And the coolest application that I really like is this wireless device that we've been developing. So today in ultrasound systems, because of the high rates, basically the doctor holds the probe. The probe is totally analog. So you scan with the probe, it transmits the pulses and receives them, but it then goes, there's no digitization. It goes through this cable into the machine, and only in the machine do you sample and process because of the high rates. Now, due to the fact that we can now sample at much lower rates, we could do it directly within the probe, and that allows us to totally get rid of the machine. So there's no longer a machine. We sample within the probe, we send the data wirelessly over any standard Wi-Fi channel, and then you could recover, either on a tablet that the doctor is holding, or you could send the information to the cloud to do more elaborate processing like deep learning, etc. So let me quickly show a prototype that we've developed in the lab.
I would like to show you here a demonstration.
So here we're showing the probe that we've developed. This is a cardiologist that we're working with, Dr. Shai Taimaniardet, and he's scanning one of my students.
In which we can see right now.
So this is just for powering purposes. The data is going directly from the probe to the local machine, to a tablet, and to a remote machine via the cloud.
The mitral valve and the tricuspid valve. We can see the nice motion of the leaflets. We can see that actually there is good ventricular function and there is no pericardial effusion. The picture itself is very good, very crisp, and we can demonstrate very nicely this subject's heart.
Okay, now you see him scanning directly to the tablet. Now, what's nice here, besides the fact is that we have an entirely new cheap ultrasound experience, is that this enables access to the actual data. So today in ultrasound, what you get as an output is the image. But using our method, what you get as an output is the actual channel data, right? This is pre-processed data. And once we have that data, we can apply more sophisticated methods like deep networks onto that data. And that gives us, of course, much better imaging. So not only do we have a smaller, cheaper, more efficient device, but we're actually getting much better images out of it. Now, what's further interesting is that this channel data has information in it beyond just an image, right? So an image is a particular way of depicting the information in the channel data, but we've begun a clinical forum actually dedicated to looking at what information is in this data now that we have access to it that might not be in the form of an image. So to me, this was a very interesting experience where basically, you know, we started with looking at doing acquisition more efficiently, but this actually paved the way to entirely new clinical applications just from the fact that we now have access to data that people didn't have access to before. So we have many doctors that we're working with on this, and we have some beginning of results, but you know, I don't want to show things that are not yet clinically finally approved, but hopefully the next few months we'll have some clinical publications on this, which really are focused on the channel data themselves. Okay, so that was ultrasound. We could do the same thing in radar. So radar is very similar to ultrasound. Maybe in the interest of time, there's a movie here. I'll skip it. You can find it on my webpage. We also have a recent book focused specifically on radar where we go through some of these applications. I'll just show the beginning of this, and then whoever's interested could see the movie on my webpage. But basically, very similar to radar, we try to attack these trade-offs between, you know, bandwidth and resolution, both in frequency, in space, and in time. And when we can show that using very similar techniques to what we've shown in ultrasound, we could develop radars that are very efficient, need a small number of antenna elements, and could get better resolution and sweep more areas than you could get from a standard radar. So this is the actual radar system. But again, in the interest of time, I'll skip through the movie, and those of you interested could see it later on. So one of the things, just to say a little bit about the applications, one of the application that we're looking at in terms of radar is automotive radar, which of course has many challenges. And one of the challenges is the ability to look, you know, all around you very efficiently. So because we know how to be more efficient in terms of our resources, we built a prototype where we could look at multiple directions simultaneously, whereas a standard radar would have to scan them one by one. So we're doing basically spatial mixing here and getting multiple directions at the same time, where each direction, of course, we're doing at a sub-Nyquist rate, and we're actually getting better resolution. So we have sub-Nyquist in time and space, but improved resolution, again, by exploiting the models, the same models that we talked about in the context of ultrasound. Now, what's very interesting in the context of radar is that in ultrasound, basically we know the pulse shape, but in radar, what often happens is that we transmit a pulse, but it gets very distorted because of the environment, so that when the pulse comes back, we don't actually know the pulse shape. And this leads to an interesting mathematical problem. If you look at the basic stream of pulses model, the finite rate of innovation model, the sub-Nyquist sampling assumes you know the pulse shape. But in many problems in radar, especially in automotive radar, where the environment is very busy, what we get back is a signal that could be very different than what was transmitted. So basically, we have a combination of a blind deconvolution problem with a sub-Nyquist problem. So what we were able to show here is that we could do sub-Nyquist and still recover the signal and do the blind deconvolution at the same time. But what we need are two antenna elements. So rather than doing this just in one antenna, we actually do this in two, well, it doesn't have to be two antennas, two receivers. So we have two different receivers, and that allows us to do both the blind deconvolution and the sub-Nyquist sampling. So more specifically, and again, I'm not going to go into the proofs, but just in terms of the formulation. So basically what we're receiving are two channels, two FRI channels at the same time, where we don't know, of course, the delays and amplitude. So that's the standard FRI model. But now we assume that we don't know the pulse either. We know there's a pulse, but we don't know what it is. And we can show that by doing the sub-Nyquist idea in two receivers, we could actually recover all the degrees of freedom, including also the pulse. So that leads to this demo that we've built, where basically it's the same radar demo that we spoke about before, but now we don't assume that we know the pulse shape, so the environment can be much noisier, and this is particularly needed in the context of automotive radar. And what we do is that we simply have two receivers. Okay, so we have the same board that we had before, but now we apply it twice. Here you see four receivers, because in each one we did a Nyquist one and a sub-Nyquist one, so that we could compare performance. Okay, and what we show is that we get the same performance from the Nyquist and from the sub-Nyquist. So even though we're sampling at much lower rates and we don't know the pulse shape, we could still get very good resolution, and we could still determine exactly the delays and Dopplers of the targets. Okay, so that was looking at that in the time domain. We could do the same thing also in the spatial domain. So instead of thinking about this as a sampling problem in time, we could think of antenna elements where we only want to use part of the antenna elements. And we can show that we could get the exact same advantages. So this is an antenna that we've built in the lab, and we use these sub-Nyquist principles to receive the signals from only part of the elements. And we can show that by doing this, using the design principles we alluded to, we could actually get the same performance as if we use the entire elements in this antenna. So again, here, of course, there's mathematical ideas behind this. One of the things that we've looked at is instead of randomly choosing which elements to use, which was maybe more the compressed sensing style type of view, we've actually been developing methods based on deep learning, but model-based deep learning that incorporate the model. And what we want to do is basically choose the optimal number. If we're going to use N antennas, we want to choose the optimal N antennas by tracking the target and using deep networks. So we've developed a greedy method to do this in a deep network fashion, where we're relying on the fact that the cost is submodular, so we can prove, of course, not total optimality, but at least some local optimality properties of this greedy approach. Okay, so that summarizes, relying on these ideas of structure, even if they're not entirely known, like in the blind deconvolution case, and we've shown some of the applications we can get. And what I want to move on next, which is maybe different than the standard compressed sensing framework, is looking at how we can exploit tasks, even if we don't have any structure. So what do I mean by that? Well, there's problems where we don't have any particular structure in the data, but we might have structure in the task that we're interested in. So for example, in ultrasound, the individual signals could be very noisy. So they're not sparse, or they don't necessarily have structure. But after beamforming, right after performing the task, the data is going to be structured. And the question is whether we can exploit that structure in the task or some other property of the task, even though the data that we're sampling does not have any particular structure. So what we're going to look at are 4 different applications of this. We're going to look at power spectrum estimation. So there the task is estimating second order statistics. We'll look at quantization as a task. We'll talk about quantization with and without different input structures. And we'll also talk a little bit again about this compressed beamforming notion. So let's begin by looking at power spectrum reconstruction. So here the task is we want to recover the second order statistics of the signal. And there's many problems where we sample the signal, but what we're really interested in is the second order statistics of the signal, not the signal itself. And this leads to the interesting sampling question, which is, what is the minimal sampling rate at which we need to sample a signal when what we want is to estimate its covariance? And we're going to assume that the signal is wide-band stationary so that, the covariance is well defined. And of course, it's an ergodic signal. Otherwise, we can't actually estimate the covariance from the data. So there's been some really nice recent work on this for particular forms of samplers in the asymptotic regime. But what we're interested in is looking at more general classes of samplers, and also not looking at asymptotic cases, but actually, for finite sampling rates for devices that we could actually build, could we gain when we only want to estimate the covariance? So the answer is that we actually can, and we could gain quite substantially. So before I actually show the mathematical results, I want to give some intuition as to why you should be able to gain. Okay, so there's no structure in this problem. We're not assuming anything about the covariance. I'm just saying I don't want the signal, I want its second order statistics. So to get some intuition, or at least this is my intuition, as to why we should be able to gain, let's look at this little diagram over here. So suppose, we have a signal, we want to sample it, and we have this sampling set. So the sampling set is very sparse. The density is not going to be enough in order to recover a band limited signal. But now when I say I only want to estimate the covariance, we know that the covariance depends on the time lags, right? It doesn't depend on the times themselves. So for estimating the covariance, what I'm interested in is not this set, but actually the set of all differences. Now, intuitively, of course, if I have n points, the set of differences, if I choose these points correctly, could scale up to the order of n squared. So already I'm getting more points. Effectively, I'm getting more points just because I'm interested in the covariance. And this is when it allows us to reduce the rate. Okay, so you could already see here intuitively that I could reduce the rate by a factor of square root of n. And that's really the factor that we could get in practice. So that's the intuition as to why we should be able to gain. And more specifically, we can prove that we could create sets that have a Berling density of 0. So basically their sampling rate is 0, but their different set can have a Berling density of infinity, which means that, of course, we could estimate the covariance, because that depends on the Berling density of the different set. So even though the sampling rate of the signal would be 0, we're effectively getting a sampling rate of infinity for the covariance. Now, in order for this to be the case, we need the set to satisfy 2 conditions. So it has to go to 0 slower than the square root, and we have to have enough distinct differences so that the size of the different set grows like the square of the size of the sampling set. And if these 2 conditions are met, then we can prove that we can actually estimate the covariance, even though the sampling set effectively had a sampling rate of 0. So this is an abstract statement. Now we could go ahead and look for sampling sets that satisfy these criteria. And there's many such sampling sets. Just to be concrete, we could look at a very popular type of sampling, which is multicoset sampling. So in multicoset sampling, basically, you're looking at on the Nyquist grid, but only choosing a subset of the points on the Nyquist grid. Or more specifically, you could get these sampling sets by taking the signal, introducing different time shifts, and then sampling at a sub-Nyquist rate. So what we can show is that if we only knew that the signal was band limited, then if we're sampling at an nth of the Nyquist rate, we would need n channels here, so that effectively we're still back at the Nyquist rate. But if all we want is to estimate the covariance, then we only need a square root of n channels. Okay, so that's the same square root of n that we've seen before. And this, of course, allows us to reduce the rate quite substantially. So this is very easy to show in the context of multicoset sampling. We could show this for other sampling sets as well, including the sampling paradigm that I've shown before. So we could get the same savings when we use this sampling paradigm. So one of the application areas that we've looked at for this is for cognitive radio, where basically the idea in cognitive radio is that if you look at the spectrum, it's mainly all been licensed, but many users are not actually using their licensed spectrum. So if you could identify the holes in the spectrum, you could allow more users to access the channel, and to identify the holes, basically identifying the spectrum is sufficient. So using those ideas, we've built a sub-Nyquist cognitive radio system where we could sample at very low rates, but still be able to identify the spectrum. So here we're sampling at 6% of the Nyquist rate, and we'll see that we could still get a system that could identify the spectrum even when the environment is very noisy and has different distortions. So of course, this all works in real time. It works very efficiently, particularly because the sampling rate is so low. So here you see different signals coming in. Here you see the alias spectrum, which of course just looks like junk, but after the recovery, we can actually get the signal itself. And this is very robust. It works even when there's noise and different distortions. Okay, so let me show a different application of this that we've been working on a lot recently. And this has nothing to do with sampling, but it's using the same mathematical principles. So this is the problem of super resolution. So we know that, for example, if we're using an optical microscope, we're limited to half the wavelength we've used for illumination, and that's just the basic Abba's diffraction limit. So in 2014, the Nobel Prize went to super resolution in fluorescence microscopy. And this was a really clever idea where they said, okay, if you want to get a super resolved image like we see over here, you can't beat the diffraction limit because it's a physical limit, but you could beat it if you acquire the image in a slightly different fashion. So what they do is they insert fluorescent molecules, and then they control the fluorescence so that instead of taking one image, you now take thousands of images, where in each exposure, only a small number of these molecules are actually fluorescing. So basically, you have thousands of images where in each one there's only a few green spots, and then you could just stick a Gaussian every time you see a spot and sum it up, and you'll get a super resolved image. So this works very well. It gave them the Nobel Prize. So you could increase resolution by a factor of 10, so you could get down to like 20 nanometers, which is very high resolution. But this is, of course, done at the expense of temporal resolution, because now basically to get a single image, you're taking thousands of exposures. So you can't use this for live cell imaging. You have to assume that the environment is static. And this is a very big limitation of this technique in the context of biology. So this, of course, translates immediately to a sampling problem, because the time aspect is a sampling problem, right? We want fewer images. So here we've just applied these ideas of exploiting correlation, sorry. So we're not assuming structure. We are looking in the correlation domain because these are brightness images. So instead of recovering the signal, we're basically recovering its covariance. And we've just shown that to recover the covariance, we need fewer samples. So by using these principles, we can actually get a method which we call SPARCOM, super resolution correlation microscopy, because it's based on using the correlation function. And here you see our method SPARCOM compared to STORM, which is the method behind the Nobel Prize. So you see that we use 2 orders of magnitude less data, and we actually even get better resolution. Here we can see a cavity that you don't see here in the STORM data. Now, what we've been doing more recently is actually generalizing this to model-based deep learning. So we built deep networks that are based, again, on this correlation information. And this gives us even further improvement in resolution. And it also could be used without assuming anything about the measurement system. We don't have to know the PSF or anything like that. So we're now actually applying this to different forms of biological problems. We're working with Professor Gilad Aran in the Weizmann Institute to examine the immune response of T cells. And this is work that we're very excited about because we can now see biological behavior that you couldn't see before. And we also have some other biological applications that we've been exploring with the Broad Institute. So, you know, we just have beginning of results, but hopefully in a few months, we'll be able to show concrete results for that as well. The other thing we're very excited about is using this in the context of ultrasound. So we talked about how we could use this for biology. We're also using this for imaging. Now, of course, in ultrasound, you know, you can insert fluorophores into the body, or maybe you can, but you probably don't want to. But what we could do instead is we inject microbubbles into the bloodstream. So it's just an injection of contrast agents, just like you would do in MRI or in CT. But now these flow through the blood. And when you take an image, what's hitting this image are point emitters, just like the fluorescent elements in microscopy. So mathematically, these play the same role. And we apply the same type of techniques. So in the context of ultrasound, we refer to this method as SUSHI, sparsity-based ultrasound super resolution hemodynamic imaging. Actually, the first time I presented this at an ultrasound conference, someone said that this looks like a very fishy method. But anyways, it is a fishy method because if you look over here, you see these are blood vessels that we can see very well. This is what you see from a standard ultrasound machine. This is what you see using SUSHI, using our method, and you see that you get very good depiction of the blood flow. So we're now exploring clinical applications of this, both for breast cancer detection and for patients with Crohn's disease. So this is work that personally I'm very excited about because it really gives us a clinical application of these ideas.
So we have a question in the chat.
Sure.
If you'd like to unmute and ask your question. At Agarthakoulis, I believe. Sorry, is that?
Okay, so I actually just opened the chat, so I see the question. I hope I'm interpreting correctly. So I think that the question about power spectrum estimation is whether we could use this for non-stationary data as well, like in varying frequencies and time. So that's a super excellent question. So thanks for that question. Yeah, I actually, this is some ideas that we've been looking at more recently, especially when we're starting to look at clinical applications. So of course, this is very important. So this is a really good question, and we are beginning to explore that. A natural idea, of course, is to look at different time frequency distributions like the Gabor transform. And these are ideas that we started to look at. But if anyone is interested in this, in particular, whoever asked this questions, I'd definitely be happy to talk more about this offline. So the short answer is I believe you can, but we're just starting to think about this. So I don't yet have concrete results, but definitely happy to have collaborators on this. So I hope that addresses that question. Okay, so let me move on. How much time do I have, just so I decide which topics to go through?
If you want to aim for 50 minutes or so, you have 5 to 10 minutes left.
Okay, sure. So let me kind of briefly go through quantization and how we can use that in this context as well. So, when we talk about sampling, and we're all used to talking about sampling, we always neglect quantization, right? Like the Shannon-Nyquist theorem doesn't say anything about quantizing the data. It only talks about sampling. Now, obviously, when we quantize, we introduce distortion, and that leads to the famous rate distortion theory of Shannon. But when people talk about rate distortion theory, they assume the data was already sampled. So there's kind of like these two communities, right? There's a sampling community that looks at sampling in time, but assumes infinite amplitude, infinite resolution and amplitude. And then there's the information theory or rate distortion theory community, which looks at quantization and distortion, but they assume that the data was already sampled. So what we really want is to unify the two and have a rate distortion theory for analog signals. So I won't go into details. Basically, what we did a lot of work here together with Andrea Goldsmith and her students on trying to unite rate distortion and sampling theory, where basically what we want to develop are basic limits on how well could we approximate an analog signal, where we sample at a given rate and we quantize with a given number of bits. So we take into account both the sampling and the quantization. And then the really interesting question is, at how low can we go in terms of sampling and still getting the optimal rate distortion curve? So I won't go through how we do, this is all information theory, so I won't go through how we get these rate distortion curves, but we could develop analog rate distortion curves. And what's interesting is once we have these curves, we can ask ourselves, what is the minimal sampling rate at which we need to sample in order to achieve the minimal possible distortion? Now, the point here to kind of, before we show the results, to just think about is that because I have distortion anyway coming from the quantization, there's no need to sample at the Nyquist rate, right? Like the Nyquist rate sampling says I could recover without error, but I'm going to have an error anyway because I quantized. So, why sample without error if I'm going to have an error anyway? The question really is, could I sample in a way that I have an error, but it's not going to increase my quantization error? And it turns out that the answer is yes. So what we plot here are the minimal sampling rates as a function of bit rate. And this is not assuming any structure. These are for totally arbitrary inputs. So we're comparing here, these two inputs, they have the same bandwidth. And you see that for low bit rates, I could sample well below the Nyquist rate, and I'm still getting the minimal possible distortion. Of course, asymptotically, this is going to go back to the Nyquist rate. Now, what's particularly interesting, I think, is that this already allows you to optimally sample non-band limited inputs. So if you look at this green gas markup process, it's not band limited, but for every given bit rate, there's an optimal finite sampling rate at which to sample and achieve the minimal distortion. So basically, this kind of extends the Nyquist theorem to signals that are not band limited, and it takes into account both the number of bits and the sampling rates. Now, let me just briefly, I won't go into details here because this is maybe more of an engineering concept, but it is very important in practice. And that's that these optimal rate distortion curves are typically achieved by very complicated vector quantizers. So it's a nice theory, but if we're looking at practical hardware, they're not, and this has nothing to do with this sub-Nyquist part. This is true for Nyquist sampling as well. So the next thing we wanted to look at is whether we can use practical ADCs. So for example, low bit, simple scalar quantizers, which is what people actually do in practice, and still be able to achieve the optimal rate distortion curves. So in general, the answer is no, right? Of course, you can't achieve the optimal rate distortion curve with a simple 1-bit quantizer. Otherwise, people would have done that a long time ago. But what we exploit here, again, is this notion of a task. So what we come up with are these what we call task-based quantizers, where we say, okay, we're going to sample and quantize an input, but what I want is some specific tasks. So for example, in communication, I'm going to sample and quantize these analog signals that I'm receiving, but what I want is to recover the bits or to estimate the channel, right? I have a particular task in mind. And what we can show is that by using simple scalar quantizers, but first doing analog combining. So you could think of this, in compressed sensing, for example, right? We mix before we sample at a low rate. So here we're doing something very similar. This is not from a compressed sensing point of view, we're not assuming sparsity, but we're still combining all of the information and then going through simple scalar quantizers. And we can show that by joint optimization, so we jointly optimize the analog combiner, the quantization level, which is the only thing really you could optimize in a scalar quantizer, and the post-processing, we could achieve the optimal rate distortion curves, even though we use very simple scalar quantizers, even 1-bit quantizers. So with 1-bit quantization and an analog combiner that's linear, so all of this is simple to do in hardware, we could actually achieve sub-Nyquist sampling and sub-Nyquist quantization, where we're not assuming sparsity, we're only taking into account the specific task that we have in mind. So let me skip through the math again. Anybody interested, I could follow up with some relevant references. And we've applied this in particular to massive MIMO systems where you have multiple receive channels. So this is very costly from a hardware point of view. And we've shown that in each one of these channels, we could sample at a low rate and we could quantize at a low rate and still get the optimal performance as if we used all of the channels, 16 bits on every one of the channels. Now we can also do this without even knowing the channel statistics. So this is an example of a model-based network where we kept this overall structure, but we introduced learning into each one of the elements, and then we could get the same performance without even knowing the channel statistics. So this is a demo we've built of that. I'll skip through the details, but here you can see the basic idea. So this is the analog combiner and the hardware that we've built for that application. We've also been looking more recently at doing this analog combining using metasurfaces. So this is a flexible way of actually implementing this that is very efficient in hardware as well. So just the last thing I want to say in this context is that we've talked about how we could do radar efficiently, how we could do communication efficiently. And an area that we've been looking at a lot recently are joint radar comm networks, where basically we're doing both of them efficiently, and therefore we could do them on joint platforms. And this is very important, let's say in automotive systems where we have both radar and communication, and we don't want to have separate networks for them. So we're now building prototypes where we do the radar and comm together because each one of them is more efficient. So finally, just one last thing before we say two words about the model-based network is that we've also been looking at using this for federated learning. So those of you familiar with federated learning, it's basically a way to do distributed learning where you don't share the actual data, but rather you share the gradients of the network. But of course, sharing the gradients could be costly as well if you're doing this for many users. And by using these task-based quantizers, we can actually, again, show that we can do 1-bit quantization of the gradients and still achieve the optimal performance in the central network. And here, of course, the task is that you're learning a deep network. So again, you're not interested in recovering the information of each user. You're only interested in training the actual network. So that's just another example of these ideas, which again, these are not sampling problems, but we can use these same ideas for interesting learning problems. Okay, so let me take 2-3 minutes to talk about, how we use these ideas in the context of model-based learning. We've seen some examples kind of throughout, but let's make this a little bit more systematic. So, of course, everyone's aware of the deep learning revolution, so I won't waste time in saying anything about that. We're also all aware of the challenges, right? It's not clear really how well it generalizes, how interpretable the networks are. We need large training sets and so forth. Now, when we think about signal processing, so signal processing is typically model-based, right? We have a model, everything is nice, and we could quantify everything. We could develop optimal solutions. They're typically, rather straightforward to implement. We could assess the quality of the output. So we have very nice theory, but of course, this requires accurate model knowledge, which we may not have. And it can also be quite slow, right? The problems could become complicated and it could be quite slow to do inference. So a theme that we've been looking at a lot in recent years is trying to combine the two, is saying, okay, could we get the benefits of the model-based ideas and of learning at the same time? So to just get a sense on a high level view of how we would do this, if we try to kind of abstract model-based processing, we could think of, having an input Y, which is our measurement, having some desired output X, and having a well-defined function that connects them. So we know that Y is equal to some function of X, and then we're going to use some metric, which we denote here by F, and we're going to try to optimize this. And, let's say we use our favorite iterative algorithm to do this, and it will typically consist of some pre-processing, some post-processing, and then it's steps of iterative steps or gradient steps of the algorithm itself, which also typically have some generic computation, and then there's some block that actually depends on the model. Now, if we look at deep learning, of course, the framework is very different. What we'll have are many inputs paired with many outputs. We'll use that to train a prefixed network. So this network has nothing to do with the problem. It's prefixed. We're going to train the weights. And then when we have a new input, we hope that it will, miraculously predict the correct output. So, this is, of course, an abstraction, but it shows how different these two paradigms are. Now, how could we combine them? Well, we combine them in two ways. So one way is by looking at this as an iterative process and trying to learn the iterative process. So that leads us to these ideas of deep unfolding. The other way is by just looking at the block that depends on the model and saying, you know what, every time there's a block that depends on the model, I'm just going to stick a deep network inside. So these are kind of two ways that we combine model-based with deep networks. And all of the applications I showed throughout the talk are basically based on these two ideas. So let me just very quickly maybe outline a little bit more of the steps and stop me when I'm going over time. So this idea of unfolding dates back to Gregor and LeCun about 10 years ago. And somehow it took some time till people picked up on it. And now we've been looking at this a lot and generalizing it in various different ways. So the idea is that you take your iterative algorithm, you specifically write out several steps. So let's say T steps of the algorithm. And then what you do is you free the parameters in these steps that you don't assume are known, and you learn them from data. So this leads to this notion of unfolding, and we recently wrote a review on these types of techniques and some of the applications. So those of you interested could see much more details there, including, you know, some theoretical results that you can say about these types of networks. So we've applied this to many different problems. I won't go through the applications. We've applied this to denoising, to deblurring, to super resolution ultrasound. We've applied this to separation. So you could think of doing a robust version of robust PCA where you don't actually have to know the model. And actually, just as a funny thing, in this context, we called the method convolutional robust principal component analysis, Corona, and this was back in 2018 before Corona, so it looks like this method kind of went viral. But we've been using this a lot in ultrasound to separate, let's say, blood flow from tissue. So there's a lot of different games you could do about this. Those interested in ultrasound, we have a recent review specifically on how we use these ideas in the context of ultrasound. For the second approach, like I said, what we do is we look at the blocks that depend on the model and substitute only those blocks with the network. So one particularly nice application that we're fond of that we looked at is what we call a Viterbi net, where we looked at a Viterbi decoder and we use this to just learn the likelihood block. And we've looked at various different applications in communication. So again, I won't go through that. But let me just say that we recently wrote a review on this as well. So those of you interested could look at that. And finally, just last slide, we've also been using these ideas in the context of COVID-19 detection. So we've recently been working with a group of clinicians throughout Israel to use these types of model-based networks for detection of COVID in both X-ray and ultrasound. And right now in X-ray, we get over 90% detection. So those are pretty good results. And we're in ultrasound, we're lagging behind. I think right now we're like at 78%, but we're improving those. So hopefully we'll get there as well. Okay, so let me wrap up. We've tried to show that if we want to get, you know, efficient, interpretable, high-resolution sensing, we have to take into account everything we can, and we focused here on the structure and the goal. But you could definitely think of other ideas you may want to take into account. And the particularly important thing is looking at this holistic design. We've talked about mathematical limits that we could get, different engineering research, engineering developments. And for us, particularly, what's particularly exciting and what we're focusing on now is looking at different scientific and clinical breakthroughs that you could get now that you could acquire data more efficiently. So let me just end by saying that I know I've skipped through a lot of details. I wanted to give kind of a high level view. You could find more details on our papers and our books on these topics. And of course, none of this would have been possible without my amazing team. So you can see that this is a recent picture. We had an outdoor event, everyone masked, of course. And of course, my amazing collaborators that I have the privilege to work with. So thank you very much for your attention, and sorry if I went a little bit over time, and definitely happy to stay on for questions.